Hello. In today's experiment we are going to try to find out what's going on with the asymmetry. Yesterday I got some good results, so I could actually read the tape, but the signal is asymmetric, so if I push out 50% duty cycle, in return I get something different. And as it turns out, the tape doesn't really have to do with that. So for example, if I put out 4 kilohertz, this is not really visible, but if it's, for example, 10 kilohertz, that's already different, that's quite visible, and probably 20 kilohertz is the worst offender. So what's going on? One of the stranger things is that currently the inputs are not even connected. These resistors, they are the inputs of the op-amp, they're not connected to anything, but the signal still can be very clearly seen on the scope, the output signal. This is the digital signal that the Pi Pico puts out, and it's perfectly symmetrical. It has absolutely no problems. Maybe if we find out why we are getting any signal on the input at all, maybe it would help us understand why it's also asymmetrical. So the first cascade has its output at pin 1 of the first op-amp. Pin 1 is really busy, so instead I am going to probe between the first and the sixth pin. The signal is pretty weak at this point, so maybe we should try and increase sensitivity. I don't really know how to interpret this. What happens if I stop the tone? Nothing. I begin it again at 10 kilohertz, and this is what I'm getting. It picks it up from somewhere. So it could be the power interference or just some parasitic capacitance or inductance in this rather messy circuit, because this is what it looks like. Another possible route for the signal is basically radio. Here, this is the so-called output amplifier in quotes, which is a hex inverter, and this is its output number 1, which goes all the way over here, and since the head is currently disconnected, it just doesn't go anywhere, and the other side isn't loaded to anything, so it's kind of a huge antenna. So I will try and disconnect it at the source. So I have disconnected both wires, and what we are looking at now is fairly quiet signal here. So the next thing would be to see if we still get something on the output of the amplifiers, because, well, we don't see anything after the first stage. It doesn't mean that there is nothing at all. I will just remove it from here. We don't see anything. That's fantastic. So a new idea. I have connected the output directly to the input. The output of the first stage is looking like this. It's symmetrical. I really like it. I can try it with a high frequency, like no, it's not ideal. At 20 kilohertz it looks nice. At 30 it seems to hit the floor, no? So maybe this is the reason why we are having some asymmetry. Probably not at this stage, maybe at a later stage in the amplification. We hit the floor, and that's how I get asymmetry. So one thing that I know is the virtual ground, which is created here. It's not symmetrical, it's offset down a little bit. This resistor divider, it sets it at around 2 volts. The reason for this, I think the op-amp, this is LM358, it can work at 0 at the lower rail, but it cannot really reach the higher rail. It wouldn't hurt if I tried to shift it a little bit higher and see if it changes anything. To do that, I'll have to change this divider, which is assembled at this corner of my breadboard. My precious LEDs. Turn it on. It's not perfect. Did it get better or not? Here's something. I think it has become worse because I was looking at 20 kilohertz, and although this is the output, this is not the first cascade. At 10 kilohertz, it's more obvious that the asymmetry has become worse, and actually at 4 kilohertz, it has become completely useless. So probably I am on the right path, except that I should dial it the other way around. I should probably offset the virtual ground a little bit lower. Let's browse the great book of resistors. I need 2 kilo ohm. The original was 2.2. Okay, so I will try 2K. And with 2K, the symmetry, at least I think it restored. It's back to semi-normal again. At least at 4 kHz it looks nice. At 30 kHz it looks alright. At 20 it isn't, so yeah. So I will try to shift it even lower and see what happens. The next value in the great book of resistors is 1.88. Is it better or not? That's a great question. I think it's the same. Maybe I should try more extreme. 1.5. And the same question again. Did it become better or is it the same? I think it could be a good idea to check out what's going on with the actual tape signal. It's on. 4 kHz look probably the same. Oh, by the way, the scope reports duty cycle. It says 45%, and that's bad. Let's see what 8 kHz look like. 40% duty cycle. That was useless. What we're going to look at now is the input of the third stage. So this is pin 2 of the second op amp. Let's hit play. Interesting. I thought it would be significantly larger here. Maybe here's the problem. Maybe the amplification is just not enough for the comparator to pick it up, and the slightest offset causes the asymmetry. Let me try and plug at the next stage. So pin 1 was kind of overbooked, so this is pin 6, the input of the comparator. And hit play. Yeah, I don't know, it looks really nice. It looks symmetric. There is nothing terrible about this signal. It's why it looks like a triangle. Okay, if I did not miss the hole, the amplification should be obnoxiously huge. What is happening at the output? Ooh. So let's see what's going on. Not at the output, but again at the input of the comparator, because I kind of liked it. It looked like a triangle with smooth corners. Oh, now this is clipping. And is it good or is it bad? Probably it doesn't really matter, because this is the comparator and, well, it compares with the middle here. Let's see what's going on here at the output. And it's still fairly asymmetric now. Just to make sure, this is the middle. This is what the comparator is supposed to compare it against. And does it measure it? Yeah, it says that currently it's at 1.55 volt. And this is the input of the comparator. The comparator has a slight hysteresis to it. There is a 2.2 meg resistor in the feedback. Could it offset the point that it compares against a little bit? What happens if I just remove this resistor? I think it makes sense to probe the output, because the input is kind of here as much as we can see with the scope. It's alright. It's something that's happening presumably at the very last stage. What I'm seeing, that's the input noise that's being constantly compared against the middle with the comparator without any hysteresis. And let's have a look what it looks like if the tape runs. Yeah, play. I think when the actual signal starts, it will pick it up and it will dominate. Yeah. So it shows still the 45. Yeah, 45 duty cycle, 8 kilohertz. It's about 40. Again, nothing really changed. Maybe I could try increasing the hysteresis. I have replaced the 2 megohms with just 1 meg. Duty cycle 45 and the same. It didn't help. 40% duty cycle at 8 kilohertz. So it did not help here either. I used to measure the output after the 2 stages of the Schmidt trigger. This is 7414. Here I am looking at the comparator output and it's 4647. And if I look at the output of the first Schmidt trigger, I get, okay, 56. That's the same thing, just flipped the other way around. But let's wait until it goes to 8 kilohertz. So we are looking at the output of the first Schmidt trigger. And here the duty cycle looks kind of like it has worsened a little bit. Right, here's the input, 43 for example, and here's the output, 60 something, and here's the final output if I still get it in time, and it's 30 something. Maybe the problem is in the input levels of the HC series, because it's CMOS and the original used LS, and probably something about the input levels can just make it asymmetric. It's more about being in the middle of the valid input range of the Schmidt trigger. If in LS it's around 1.2 and in HC it's around 2, I should probably move my virtual ground higher up instead of moving it lower down, and maybe that would help. So it was a very frustrating evening last night, and I decided to sleep over it. And I've been thinking about probably adding some offset to the comparator, so that here or here I could offset the input a little tiny bit, and probably that would help the duty cycle. Maybe that would make it more symmetric. But then I remembered that it's getting worse after the Schmidt trigger, and the middle value of the hysteresis was suspect. And then I remembered about this little guy here, and I don't really know what exactly it's doing. It's kind of probably it's similar to this one or this one, so it's just providing a load to the op-amp. But then I realized that you don't really have to load it on the ground, you can load it on a positive rail just as well. So I decided, why not just give it a try and pull it up. And here goes. 25. I have just moved it a little bit so that it's now pulling it to +5. So let's see how it works now. And hit play. Maybe the offset that it gives now will help even out the wrong offset that we had before. And what do we see? Hey, look at that. It shows 50 duty cycle, 50%. And it's a win, because if it's really 50%, that's amazing. That means that we have won. Probably not by, well, I don't know, maybe we have righted one wrong with another wrong, I don't know. 8 kilohertz, it's also showing 50%. Amazing. If I had it from the very beginning, I wouldn't suspect anything at all. So it works. Let's wait for 10 kilohertz. 10 kilohertz, 50% duty cycle. Hooray, we won. That's perfectly usable. So I will probably just keep it. I will update the circuit so that it reflects the actual state of things, and yeah, I'll just have to keep it. And later we will see if it really works with variable pulse lengths. I'm not sure what we're looking at currently, so let's just fast forward. It should show some higher frequencies written at rewinding speed. Yeah, 20 kilohertz. And by the way, it looks perfect today. I thought I had some dropouts, but they are not dropouts now. But not 30 kilohertz. Okay. Nice. I think this concludes the current experiment. Thank you for watching. Bye.